Hello, welcome to the second part of the VIS2 course, visualization. This part will be about volumes. What is a volume in the context of visualization, and what is a marching cubes algorithm. Algorithm was a very strange name, but in the end hopefully you will understand why it's called like that. First of all, what are volumes in this context? Volumes are three-dimensional blocks of data. So we have data values, one small cube here, and in the volume on the right, one small cube here is one data value, and we have a number of them in three dimensions, in the x direction, in the z direction, and in the y direction. So each point, each small cube here represents one single value, which is probably coming from a medical scanner, like an MRI scanner or a CT scanner. So each little cube here is one single value, which in this context we call a voxel. A voxel is short for a volume pixel. A pixel is usually for a 2D image, photo, with only two dimensions. That's what we call a pixel. One point in a photo is a pixel, but this is one point in a big three-dimensional volume, and that's why we call it a voxel and not a pixel. A scanner usually generates, it scans your head or it scans your body, and then it generates a number of these voxels, one value for each point in the 3D space. So we can say that one voxel represents one single value or a sample in a 3D grid, a three-dimensional grid. The volume is three-dimensional. The values that we are talking about can be one single value, like opacity at that point, or it can be a color, which is actually three values, and like you know, it's a red and the green and the blue component. It can be a vector data. It could be a direction of flow of something. Then we also have three components, an x and a y and a z. So it depends a little bit on the situation what kind of data we have in a voxel. It can be a single value, it can be a color, it can be a vector, or something else. In a CT scan, for example, these values are what we call Hounsfield units. So they represent certain values that we call Hounsfield. And the Hounsfield value corresponds to, for example, bone or blood or other tissue, muscle. Each of these tissues, they have their own Hounsfield value. Blood has another Hounsfield value than a bone or then a muscle. So often when the volume is coming from a CT scan, we talk about Hounsfield units. A volume is like a cube. It has a width and a height and a depth. The point is that we don't want to see that cube, but we want to see the object that's inside it. So if I go back to this example here, we have a cube of data, and the scanner gives us a value for each small voxel, but actually what we want to see in the visualization is not the whole cube. That's not interesting. We want to see what's inside the cube. We want to see the head, or maybe we even want to see inside the head the brains. So that's our goal. To specify in some way which part of the volume that we want to see, not the whole cube, but an interesting part of that data inside the cube. And it's often the case that we want to show, for example, voxels that have a value that's bigger or smaller than a certain limit. Show me all the voxels that have a value bigger than 100, or all the voxels that have a value between 100 and 120. That's something that you want to do with the volume. You don't want to show the complete cube, the whole volume, but a certain part of it. And then, in order to really render the volume in a graphical card, we have to convert it into polygons. As you know from the V3D1 classes, our graphical unit, our GPUs, they can handle polygons very efficiently, and they have no clue what a volume is. So in order to really see something on the screen, the volume, the block of data, has to be converted into polygons that can be rendered by the GPU and then shown on the screen. And for that, several algorithms exist. The one that we will look at today is, as already mentioned, the marching cube algorithm, marching cubes. But there are others like volume raycasting that we'll do later, and splatting and more. But all of these, what they have in common is that they take a cube of voxels, a cube of data, and filter out certain parts so that you can see what's inside the volume. So then, what about these marching cubes? It's, as I said, it's a way of rendering a volume, showing what's inside the volume. And what we actually do with the marching cubes algorithm is create a so-called isosurface. An isosurface is a surface inside the volume that is made out of all the voxels that have the same value. So you can make, for example, an isosurface for voxel value 100, and that will show you as a surface all the values that, all the voxels that have a value of 100. So back to the example, it could be that all these voxels here in the around the head, which is actually just air, they could have a voxel value of 10, each of these. And then the voxels that are on the skin of the head, they could have a voxel value of 100. Just an example, I don't know the exact values. And then if you make an isosurface of value 100, then you would see exactly the skin at the outside of the skull. The isosurface 100 in that case would be the outside of this skull, and then all the voxels around it would be ignored because they have a lower value, and you only see the outline of the skull. And that's what we want. We want to filter out uninteresting voxels like these around the head, and we only want to see the interesting part, let's say the head. So that's what marching cubes do. That algorithm creates an isosurface, also often called a contour. And when you want to use an isosurface, when you want to use the marching cubes algorithm, you also always have to specify a value. You say, I want to see all the voxels, I want to see the surface, the isosurface of all the voxels that have a certain value, like 100 or 50 or 200. It depends, but you always have to specify that value. And then that isosurface will be converted into polygons, which can be shown on the GPU. Well, then, how does that marching cubes algorithm work? In order to explain that, we simplify the situation first a bit to a flat plane instead of a cube, instead of 3D. I'm going to explain how the marching cubes algorithm works by first looking at a 2D situation. So let's say that this is our volume, only a flat 2D grid. So this is, you could say this is marching cubes in 2D. And let's say that in we have these values, these are measured values. At this point the machine measured the value of 0, and here it measured 1, 1, 3, 2, 3, 6, 6, 3, 1, and so on. These are the values that the machine measured. And let's say we want to make an isosurface for the value 5. Well, actually there is no 5 in the whole grid. All the values that the machine measured are either bigger or smaller. There is no 5 in the whole grid. But still we can make a guess where the ISO contour of 5 is going. For example, it's probably going here in between the 3 and the 6. At this point the machine measured a value 3. At this point it measured 6. So probably somewhere here we have a value 5. We interpolate between these 2 points, and then we can say, well, probably here is a 5. We didn't really measure that because we only measured at this point and at that point. But at this point there is probably a value 5, and here's a 4. But we are interested in a 5. So the ISO contour will go through this point. And also it will go through this point here. We measure the 1 here and the 6 here. So in between we have 2, 3, 4, 5 around here. So the ISO contour of 5 will go from here to here. We don't know in what kind of line, if it is a part of a circle or a straight line. You have to guess that. But it will be more or less from here to here. Then how will it continue? Well, it will probably not go in between these two. This is a 6 and this is a 6, so probably everything in between is also 6. But it will go in between these two. We have 3 here and 6 here. So in between we have 4 and 5. So the line will go from here to there. And then not in between these two, because this is between 2 and 3, but then it will go in between these two. So from here to here. And then it will go in between these two. Probably halfway. From somewhere here to here. So although the 5 does not occur in any of the measured values, we can still make a guess how the ISO contour of 5 will go. And that will be more or less like this. I started here and here and here, in between 7 and 3, in between the 2 and the 6, between the 4 and the 6, between the 3 and the 8, between 2 and 7, here, and here. So this is, yeah, what the algorithm would do in 2 dimensions. You still don't get it, probably why it's called marching cubes, but that's for later. We could call this marching squares. First we look at this square, and then we say, well, the isosurface will probably go here. Then we look at this square, and then say it will probably go from here to here. Always a straight line, because we don't know what kind of line it will be. It could be more wiggling, but we assume straight lines. In this square, it will go from here to here. In this square, it will go from here to here, and so on. Well, back to the slides that I just quickly skipped, which explain more in general how that works. So what we do each time, we consider one small square. So we look at, for example, this square here. And then we check for each of the points, for each of the corner points, there are actually only 2 possibilities. So that value is either higher or lower than the value that we are looking for. So in this square here, we were looking for an isocontour 5. So yeah, this one is lower, that one is lower, that one is lower, and this one is higher. for each point you can easily say if it's higher or lower than the value we are looking for. And when you do that, it turns out that you have actually only 4 possible configurations. It could be that one point is one point is higher or equal to 5. C is 5 in our example. And the other 3 points are lower. And that's actually the case for this one. And we have 1 which is higher, and we have 3 that are lower. It's this situation. It's a bit rotated. In our specific example, the higher value is here, and now it's here. But that's only a rotation. It's basically the same situation. And in that case, you know that the line will go in between these two, because this one is lower, that one is higher than 5. C in general, but in our example 5. So the line must go in between these 2 points. And same here. If I have one higher and one lower, the line must go in between these 2 points. And not in between these two, because they are both lower. Not here, because they are both lower. So the line will be something like this. You can also have situations that 2 points, 2 neighbor points are higher and 2 are lower. Then you know the line will go from here to the opposite side. And maybe not in this direction. It could also go down or go straight. That depends on the actual values here. But you know, if this one is higher and that one is lower, the iso line will go in between these two. So, for example, that's the case here. 2 values are lower, 2 values are higher. Then you know the line will go from here to here. Depends on the actual values, how low or high, where the line will go through this border. If this is a 3 and that's a 6, then the 5 will be somewhere here. If this is a 1 and a 6, then the 5 will be a little bit lower, because this range is bigger. But it's the same situation. 2 higher, 2 lower, with a rotation. If you have 2 higher and 2 lower, it can also be like this, that the higher values are not neighbors, but opposite each other, and the lower values also. Then you know that the isosurface will cross this line, because this is lower and higher. It will also cross this line, because it's higher, lower. It will also cross this line, and it will cross this line. But as it says here, this is a bit not sure how it will be exactly. It could be that the line goes from here to the border above, and from here to here, or it could go from here to here and from here to here. You cannot say that. That's, you simply don't know. That's always a guess. If you apply the algorithm will choose for one of these two, but you can never be sure if it is right. And the last situation is that you have 3 values higher and 1 lower. Well, then you know that the line will cross this border and this border. So it will go something like this. Or here, or here, or whatever, but it will go from this border to that border, and not here, and not here. So this is the general situation. There are actually only 4 possibilities. For one of them, it's not clear what it has to be. You simply cannot know. You have to guess it. It could be a wrong guess. And for the other 3, it's quite clear. So that's what we did here. We did not meet this situation, but we had, let's see, yeah, we have all the other situations here. Yeah, so here is a square that has 3 values higher than 5, 1 lower. So that's this one. A situation where the ambiguous case also occurs, so 2 values higher opposite each other and 2 values lower opposite each other, is, for example, here in this square here. We have 6 and 7 higher than 5, opposite each other, and 3 and 3 lower than 5, also opposite each other. And here we don't know. As I said, we don't know. It could be this, or it could be this. Again, you cannot know. You just have to make a choice and hope that it's right. The ISO contour could be this one and a circle around the 3, or it could be this. So that's an ambiguous case. We cannot avoid it. This is a 2D example. In 3D it's actually the same, but yeah, using 3 dimensions, which means that instead of generating these lines, we are going to generate small polygons. And that's what we need. Our goal was to convert the object inside the volume into polygons, which can be rendered on the screen by the GPU. So in the 3-dimensional case, if this is not a flat square but really a cube, also a depth dimension, then each line here will actually be a polygon. So then we move to the marching cubes instead of marching squares, which means that instead of a square we consider cubes. But we actually do the same. We have values which are measured in the corners of the cube, and there is a value we are looking for, C. Let's say 5 again, and we want to create the isosurface of value 5. Like in the previous example, we want to create an iso contour of value 5. Now we want to make an isosurface. And for each cube we check all the 8 corner points. So there are 8 now in the cube, not 4. And there are 2 possibilities. The measured value in the corner of the cube is either smaller than the value we are looking for, or bigger or equal. And that gives us a number of different situations. Like here we have 1 point which is bigger, 7 points that are smaller than the value we are looking for. So then we know that the isosurface we are looking for, it will intersect this line, it will intersect this edge and that one. Because this one is bigger, that one is smaller, so then the value C has to be somewhere in between, and here and here. But it will not cross this edge, for example, because these are both smaller. So then the isosurface, as it intersects this small cube, will have more or less this shape, this triangle. Okay. It intersects this edge and that one and that one. So in that situation, 7 points inside and 1 point outside, the isosurface will be located like this. So this is the one part of the whole isosurface. I imagine that this cube that we see here is like one square over here, but now not a square but a cube. When we analyze that, it turns out that here we have to consider 15 different cases. So there were 4 different cases in the square, in the 2D situation, and there are 15 different cases in the 3D situation. It's much more, but still manageable. You can easily make a program for that, and it's not that many different situations to consider. So this is the one that we just saw. 1 outside, 7 inside, and we have this kind of isosurface. Here we have 2 outside and 6 inside, 2 bigger and 6 smaller. Or these 2 bigger and the other 6 smaller. And these are all the different situations. Well, there's a video here that shows it, so let me run that. You see a volume with the smaller cubes inside, and you see that for each small cube the algorithm finds a part of the isosurface. So let's run it again. This is the big volume. Here are the smaller cubes, and now for each of these small cubes the algorithm finds a part of the isosurface. And hopefully now you see why it's called marching cubes, because we handle the cubes one by one. We are marching through these cubes and each time generating a part of the whole isosurface. Done. And then the result is this. We have two objects which are the isosurface that we are looking for. And the isosurfaces are now made out of polygons, so that's nice. They can be rendered easily on a graphics card. Okay, well, that's the algorithm. That's how it works internally. Luckily we don't have to program it. It's all done by other people, much smarter than us probably. We implemented this and they put it in the VTK library, and we can just use it. There is a filter called VTK marching cubes that does exactly that, what we just saw. As you can understand, we have to define a value. We have to say I want to see the contour for value 5 or for value 100 or whatever, and then we can run this VTK marching cubes filter. It's also called VTK contour filter, which is basically the same, another name for the same filter. As the name says, it's a filter. So in the VTK pipeline, it's coming after the source and before the mapper. So now we have, for example, here a source which is a reader. It reads volume data from an SLC file, vwknee.slc. So this is probably a scan of a knee of a person, saved in a file with the SLC extension. And this reader will read that file and send it into the pipeline. And this is a volume, basically a cube, a big cube. We want to see only the knee inside that cube. So we use our filter, marching cubes, filter VTK marching cubes, to generate an isocontour inside that volume. The VTK marching cubes has the ability to generate more than one contour at the same time. So we have to specify how many contours we want to generate, in this case only one. And we have to specify for which value we want to generate the contour, in this case 100. We have only one contour, which automatically has the number 0. So this means set value 0, 100. Contour 0 must be the one for value 100. That's the isocontour for value 100. If you would set a number of contours to 2, then you would also have to say cFilter.setValue 1, comma, the other value for the other contour. So then 1 would be the number, the identifier of the second contour, and 0 is the first contour, 1 is the second contour, and then you would have to say what the value is for the second contour. So for the first contour it's 100, with 1 comma, let's say 150. You say that for the second contour has to be made for value 150, and then this filter, VTK marching cubes, can generate 2 of these isosurfaces at the same time. We connect it to the reader, and the input of this one is the output of the reader, and then this one, the cFilter, is again the input for the mapper, and after the mapper we have, as always, the actor and the rendering, and the renderer and the rendering window, and so on. From there on it's the same as before. The only addition is that yeah, we add this filter. It filters the volume. Instead of seeing the whole volume, which is a big cube, we filter out one isocontour or two, in this case one, and that will be shown. We end with a small demo. This is basically the program that you saw in the slides. It opens the knee model, calls the VTK marching cubes. We have one contour. We want to see the contour of value 50. We connect it to a filter, mapper, actor, renderer, render window, and render window interactor. So if we run this, what we see is a surface that belongs to the value 50. Here it is. It's an object. I can rotate it. And yeah, these are, what we see here in red are all the values. All the voxels that have a value of 50 connected as one surface. Why is it red? Because I did set the color to 100, which is red. Why was it a bit transparent? That's because I did set the opacity to half. If I don't specify the opacity, then it will be non-transparent, like you see here. Maybe a bit clearer. So these are all the points inside that voxel, inside that volume, I mean, that have value 50. And they are shown in red. And instead of showing one contour, I can also show two, which is another C filter dot set value, but now for the second contour, number 1. And let's say that we want to see the isocontour of 70. Here you see, now we have two contours. You still have the first one, the skin, but apparently 70 is the value for the bone. So now we also see the bone inside the skin. And if you want to see only the bones, then we have to set the first contour to 70. And now we only see the bones. Contour 70. By the way, this, which you see here, it's not a part of the body, but it is a tube that the patient had sticked on his leg at the moment that the scans were made. So this is a plastic tube. It has apparently the same value as bones. So that's how it works. If you use two contours like we had here, 50 and 70, two contours, then they both have the same color. And that's what we saw. The skin and the bone have the same color. That's because this VTK marching cubes, it generates one object. The two contours are combined into one object, and we can give it one color, red. If you would want to give the skin another color than the bones, then you would have to apply the marching cubes twice. So let me do that by undoing a few steps. Here, and now I applied two filters. Sorry, this has to be one. Yeah. I applied two filters, one for the value 50 and another filter for the value 70. So it now are two separate filters, which also each have their own mapper, their own actor. And then I can say, well, I give one the color red and the other one the color green. So in order to do that, you need two actors and therefore also two mappers and two filters. So then we get this result here. And the skin has another color than the bones. because they are the result of two different filters. Suppose you want to do that. Okay, this is it for the demo.